Okay, talking about vectors in Rm. Okay, now, two-dimensional space is R2. That's what we just looked at. Three-dimensional space is R3. That's what we're going to be using in this course. So I'm just going to go to Rn because it's an easy extension. Okay, so if n equals 4, you've got 4 components, you put an arrow over it. Okay? Now, anybody want to conjecture what's the magnitude of V? How do we do the magnitude in R2? Well, we took the square of this component and the square of that component. The components are 2 in, let's say, the x direction, -5 in the y direction, 7 in the z direction, okay? And x ought to be this way, z this way, we'll see that. But now, we got another dimension which I can't visualize, okay? Anything we visualize in three-dimensional space is going to have components in the x, y, and z directions. And these components have to be independent. They all have to be orthogonal, which is like perpendicular, but it's a more general term that applies to any dimension, okay? So orthogonal basically means perpendicular in this course. In linear algebra, orthogonal means something different. It means your dot product is 0. And you should remember that if you had some linear algebra. Okay? So anyhow, the magnitude of V, and I know most of you did, magnitude of V is going to be defined. In linear algebra, we just do it as a dot product of V with V. But here, it's going to be square root of 2 squared plus -5 squared plus 7 squared plus 4 squared. And what's that add up to? Let's see, that's 4, 29, and 49 is 88, and 15. I think that's square root of 105. And I just did that in my head spontaneously, so there's a big question mark on it, but you can do it. Okay? Yeah, that's easy. Now, in 2 dimensions, you just need a single angle to define the vector. In 3 dimensions, you can do it with a single angle and a magnitude, right? In 3 dimensions, you would need 2 angles and a magnitude, like the angle with the x-axis and the angle with the y-axis, and then the magnitude, okay? In 4 dimensions, you need even more angles with them. So we really don't talk that much about the representation of vector in terms of angles. In linear algebra, of course, we developed the machinery to do this just using dot product. And since many of you probably know about dot product, I'm going to demonstrate it. Let W be some other vector. Then, without defining the dot product, that you're going to see it defined in this course, and you might have seen it defined, probably saw it defined in linear algebra, that V dot W is what? Two times -5 plus, that way there's -5 times 2 plus 7 times -1 plus 4 times 6. Okay? Now let's see, that's 10, 20, and then negative 7 brings you down to 13, and 24 gets you up to 37. Again, I'm pretty good at mental arithmetic, but sometimes it just goes haywire as heck. Didn't used to do that, but yeah. In my late 20s now, it's getting a little fuzzy. Okay.
That sounds like this.
So
I'm supposed to have the 10.
let's assume that's right. 37. We can talk about the angle between these vectors. It's the inverse cosine of V dot W over the magnitude of V times the magnitude of W. Okay, now I'm actually going to attempt to estimate this based on my unreliable mental arithmetic. The magnitude of V we found is 105. The magnitude of W is what, 25, 29, 30, and 36 is 66. So that would be 37 over the square root of 105 times the square root of 36. Okay? Now, two ways I can do this. But the square root of 105 is pretty close to 10 because 105 is pretty close to 100. The square root of 36, of course, turns out to be 6. So what we get is about 60 here. This is about a quarter of the way to 11. And a quarter of 6 is 1.5, so I'm going to say that's about 61.5. Approximately equals 37 over 61.5. And that's approximately equal to 0.6. I could probably go another decimal point, and that would probably be meaningless. Okay? But, you know, 6 goes into 36, 60 goes into 6 goes into 36 6 times, right? So 61.5 will go into 37 about 0.6 times, and I think it's between 0.6 and 0.61, I think. Maybe it's 0.61, but it's pretty close to 0.6. I'm not even going to go there. Okay. Well, that is fortunate. I just made these up off the top of my head, but that's a special angle. That's about 37 degrees. No, sorry, 53 degrees. Okay. 37 degrees is a very handy angle. Its sine is about 0.6, and its cosine is about 0.8. And 0.6 squared plus 0.8 squared is 1, so sine squared plus cosine squared is 1. Okay, just to remind you of that identity. Okay, so you'll more in physics than in here, but you'll see a lot of 37 and 53 degrees. 53 degrees being, of course, a complement of 37 degrees, so sine and cosine switch values. Okay. Little things that you should know about trigonometry, but if you haven't used it since you had it in pre-calculus, needs to be reviewed. Okay, kind of needs to be second nature. Okay, so we can do this in 4 dimensions. So it's for certain that we can do it in 3, right? And we can even visualize it in 3, and the angle really means a geometric angle. In 4 dimensions, it means something else. And I can't visualize it, and you can't visualize it. You can do projections into 3 dimensions and stuff, or even 2 dimensions, and get some kind of a feel for it, but it's usually not worth the effort. Okay? Okay. Well, that's vectors in Rn and dot product. Okay? Dot product, you just multiply each component of one by the same component of the other. Get the dot product. Everything works out real nicely. And this works in 2 dimensions or 3 dimensions. And those are the dimensions we're going to be dealing with.